Hey, so you're here for part two. If you haven't watched part one, it's linked in the description below. We have a lot going on with Swift's 20th anniversary, a new website, a small video from NASA just going over the overview of what the spacecraft is like, and so on. When I originally shot this video, it was over an hour long. And on the advice of my counterparts at NASA HQ in Sonoma State, I broke it up into 3 parts. I've learned to trust their judgment pretty implicitly. So this is part 2, getting us through the rest of the week up to the weekend, and then part 3 will air next week. So if you haven't watched part 1, watch that. Look below for more 20th anniversary stuff. Happy anniversary to Swift. All right, so Wednesday morning, relatively uneventful night. We did get 2 high priority TO requests. These are requests that will page the ODS, in this case in the morning, not right away as they are made, and require rather immediate observation. So we will see. I have not heard back yet on whether we're going to do those, but we're about to have our planning meeting, at which point they will probably be approved, and I will have to organize an upload to the spacecraft to observe one or both of these high priority requests. So about 5 minutes, 10 minutes till the morning planning meeting, I'll let you know what happens. All right, so I've gotten now an approval for that high priority target opportunity request, so I'm going to upload it. So I'll show you just how fast we can get this done. I've done no prep work in advance. This is if it just came in 10 minutes ago. Now, to explain what I did. So the spacecraft comes with a set of pre-planned observations, what we call the PPST, pre-planned science targets. We then can override that if necessary for a high priority target. The spacecraft does this automatically if a gamma ray burst or something else goes off. It detects it, it puts that into what we call the automated target slot, and then the spacecraft figures out when it can observe it and slews accordingly. So it says, all right, I can observe it for 10 minutes here. And then it says, okay, now I can observe it for 30 minutes here. And it does that. It's a very complicated operation because the spacecraft has constraints. It can't point too close to the sun, within 45 degrees of the sun, because the sun is too bright and will damage the instruments. It can't point too close to the Earth. It can't point too close to the moon. There are 2 other constraints that we like to use when we plan things, which is one, the anti-sun constraint. That, the spacecraft has these solar panels that have to be pointed at the sun. So if it gets to the point where it's 180 degrees from the sun and it slews through that, what it's going to do is do this 180 degree rotation to keep the panels aligned with the sun. That's a kind of waste of resources. We don't like to do that, so we try to avoid the anti-sun as much as possible, because then it's going to do the other 180 degrees when it goes back. The other constraint is a little more specific, which is the X-ray telescope on board had a thermoelectric cooler that is supposed to keep the telescope at a temperature of minus 100 degrees Celsius. That module failed upon launch. It never worked. And so, without keeping the telescope cool, if it gets above minus 50, you're not getting good data. You're getting a lot of noise. So what we have employed with the spacecraft is what we call passive cooling, where we try to orient the spacecraft so that the solar panels are still pointed at the sun, but the XRT heating module is pointed away from the Earth, and that keeps it cool. So we can generally keep it somewhere between minus 70 and minus 50, and that's a nominal range where it will do most of what we want it to do. So that is another constraint so there's all these moving parts when you try to plan it. We have improved that over the years with our planning software so that we can get all the constraints, make sure the slews are good, make sure the temperature is going to stay good. So it's, not as, even though it's an extremely complicated thing to do, we have models on the ground that allow us to do this relatively quickly. Over the years, we've improved upon that. We now are using mostly what I just put up, which is called a many point, where you can put up, it used to be if you want, let's say you wanted to do multiple targets. I was once on call when 4 gamma ray bursts went off in one day, and we wanted to observe them all. So I had to keep sending command after command after command to the spacecraft. Observe this burst, observe that burst, observe this burst, observe that burst. What the many point capability allows us to do is to upload a bunch of targets. And then the software on the ground will figure out, okay, here's how we want to optimize them for observation. It will then send that to the spacecraft, and the spacecraft will then consult that and say, okay, now I'm going to override and observe this target. Now I'm going to override and observe that target. Now I'm going to override and observe this target. So we can do many targets at once and don't have to be constantly sending commands to the spacecraft. We also have a continuous commanding option where we can send commands in kind of real time, almost like joysticking the spacecraft around the sky. We tend to do that when we have something really urgent, like a gravitational wave detection. So that took, about, I think it took about 5 minutes for me to do it, and half of that was me dithering about exactly how to do it. The actual software and commands were pretty quick. This is how we've been able to get to being able to handle this many requests with such a small staff, really, over 20 years, that we have these capabilities of being able to do this really quickly and automatically. So 6 hours, I wish I could have gotten it up sooner, but we'll do what we can. All right, Wednesday afternoon. The upload I set up has not happened yet, but we got another priority 2 request for an urgent observation of a target. And because we haven't done that observation yet, what I'm going to do now is cancel the many point I had scheduled earlier, and then rework it to include both of the targets that have been requested. So let's see, one was... All right, both targets are in. Now it's gonna do its magic to figure out how to get good slews and avoid the constraints and keep XRT cold. All right, look at that, amazing. Send that target out. Now I'm actually going to just check to make sure we're not bumping anything that's spectacularly important. You're not. All right, notify everyone of what we're doing. There you go. Astronomy at the speed of light. Can't beat that. Okay, so it is 2:45 Thursday morning, and I've picked the right week to record this. What we got was a LIGO trigger. LIGO is the gravitational wave detector, so it detects these ripples in the fabric of space-time that are produced by massive objects merging, like black holes and neutron stars. And when these gravitational waves are detected, we want to get a electromagnetic counterpart. This has only happened once, back in 2017. But it provided enormous insight into gamma ray bursts and how new elements are produced and so forth. So anytime one goes off, we want to drop everything and go after it. And so what it does is LIGO gives us says, all right, this big patch of sky here, that's where this, in this case, 2 black holes merging together happened. And so what we do is we start tiling it. We start making observations all over the sky, all over that little patch, getting little pieces, and then we automatically process them and look for them. So in this case, we're using the mode of continuous commanding, where we keep sending commands up to the spacecraft to, sort of joystick it around the sky to look at these things. We chose that because the next pass wasn't for a couple hours, and we wanted to get on it right away. With the continuous commanding, we can get on these right away. So we're sending all these commands. We're going to tile all this. The good news is that, oh wow, that's relatively close. The good news is that it didn't take a huge amount of effort on my part. We have a lot of scripts that do this, that automate it. plan out the spacecraft, figure out how to optimally tile that part of the sky. And so for me, it's mainly running the commands, doing the checks, and sending out the notice to everyone of what we're doing. So did take a little while to get going, but should start up. We should start doing the observations in about 5 minutes. The trigger came in at 06:15 UT, so we got our alert at around 06:24 UT. 9 minutes later, I sent the command up about 5 minutes ago, so 20 minutes, and then we'll start observing it in 5 minutes. So from the time we got the notice to the time we start observing, 30 minutes. But here we go. Hopefully something cool will come out of this. Okay, so it is Thursday afternoon, 4 o'clock. Been a bit of a day. So you saw last night we had a gravitational wave trigger. We had some issues with the plan that we'd put up, so we had to modify it. I was asleep, but fortunately one of the ODSs was awake, so they covered for me and made sure that everything got done properly. And we've been observing off and on all day, sending up various commands to the spacecraft. We also got 2 high priority requests this morning for new targets that people want us to observe right away, things that are getting explodey in the universe and need to be observed as quickly as possible. So right now I am planning an upload. So we've been doing the gravitational wave trigger all day. Now I'm going to slip in these 2 targets, get those done, and then go back to tiling the sky looking for the counterpart to the gravitational wave trigger. So and right now our colleagues in the UK and the US are analyzing the data from the gravitational wave analysis to see if we saw an electromagnetic counterpart. Fingers crossed that we do, because it was a big deal last time when we did it. It's very rare that they have them, but if they do, it could be pretty cool. So it was quite an experience to wake up this morning to 300 emails. Swift generates a ton of automated emails every time we have an unexpected slew, every time we upload a new command, every time something's going on with the spacecraft, I get an email. And because we're doing all this tiling and it wasn't planned in advance, I'm getting an email about each tile that we do. And yeah, it adds up. So when I woke up this morning and opened my email, there were 300 messages. But fortunately, I can delete most of them because they're just automated emails letting me know what I knew was going on anyway. So I'll go ahead and plan these observations for the rest of the night. We're keeping pretty busy. So until the next time. All right, so it's Thursday night, Friday morning, about 1 a.m., about to go to bed. So going through the TOOs, make sure I've done all the, trying to deal with my ODS anxiety of making sure that I've done everything that needed to be done today, sent all the uploads. I have notes for what I have to upload tomorrow or over the weekend, because we've already planned the spacecraft through then. So anything that suddenly someone says, oh, I need to get this done on Saturday, I have to plan that out. And going through the TOs we got yesterday that we now have approvals for, and putting those in the calendar so they can be observed. One of the things that's kind of frustrating with planning Swift is there are only 86,400 seconds in a day. Sometimes we are slewing, sometimes we are down, sometimes we are passing through the South Atlantic anomaly, this part of the atmosphere where the magnetic field dips in and creates a lot of interference, so we really can't collect any useful data then. So practically maybe 60 some odd kiloseconds we can do during a day. On a typical day, we have between 40 and 70 kiloseconds required. So sometimes more than we can do. So things get dropped on the floor. What's more important is that, we're observing all over the sky, and targets are not equally distributed all over the sky. X-rays and UV photons come from high energy events. And so those tend to be clustered towards the center of our galaxy in one part of sky. And so that part of the galaxy towards the galactic center has a tendency to get very oversubscribed. So that there are so many targets. We have, monitoring programs of things in there. We have things that are exploding in there that people want observed, and so on. So we tend to get more time requested for that part of the sky than we can physically give out. And so when I'm planning out these TO requests, sometimes we have a little chart here that shows how much, for the future parts of the calendar, how many kiloseconds we have planned for that day, and then how many kiloseconds we plan for that part of the sky that the target they're requesting is in. And it seems like every target this week is wanting the galactic center or somewhere close to it. And my entire board is red. There's not enough time. And so our PI, when he considers the requests, will sometimes pare requests down or assign them a lower priority, so we get a bit of flexibility in here for what we schedule, so that if we have to drop things on the floor, we know what's the top priority, what's the next priority after that, what's the next priority after that, and then anything that's left over we just can't do because we don't physically have the time. But it is frustrating as an ODS to get these requests and people want these things observed, and I'm just looking at it and I'm like, dude, not for at least a week, and by the time we get there it might be full again. So it is one of the frustrating aspects of Swift, and being the person who interacts with the scientists and has to tell them. So yeah, but otherwise the rest of today's gone good. Our uploads to the spacecraft went fine. We're still doing a lot of tiling for that LIGO trigger. Hopefully we'll find something. I don't think it's likely because we haven't found anything for 7 years, but hope springs eternal. And this is one of those things where the amount of time you have to invest is pretty high, but if you find it, the amount of science you get out of that discovery is going to be huge. So it's a high investment but high reward kind of science that Swift has been pushing the cutting edge on the last few years. So we'll see how we go. Night, everyone.